This video will focus on learning target. I can relate IMF to different physical properties of a substance. The first property we'll look at here is surface tension. What surface tension is on the top of the screen. It's essentially that layer of cohesion that exists at the top of a liquid. So it's essentially the fact that the liquid is sticking to itself. And since IMF is our property of how things stick together, really how much and how strong the force of attraction between the different particles are is how big a surface tension you have in that substance. Okay, so on the bottom of the screen you have a chart of different formulas and different substances and essentially what their surface tension is. Okay, number one thing that you can see that sticks out is how strong mercury's surface tension is. And if you think about it, that's not a molecule. So the reason its tension is so big is because they are not held together by IMFs. All the mercury is being held together by bonds, and all bonds have a stronger force of attraction than any IMF. So metals are being held together by metallic bonds, really strong force of attraction, so super big surface tension. So that's definitely number one. After that, we start to look at the other substances, and we see water has a pretty high surface tension again. And if we're comparing them based on IMF, we know that water has that hydrogen bond, which is one of our strongest IMFs, and it's super tiny and it holds together really well. Okay. After that, we have ethylene glycol down there, and if we look at the actual structure, we can see there's two places where it can hydrogen bond, and it's a pretty large molecule. So while the hydrogen bonds are not as strong in terms of the differences as in water, it's bigger, so we have a little bit of London dispersion happening, and so then ethylene glycol kind of comes next. For ethanol and octane, you can see how the size of the molecule starts to affect the fact that it doesn't have a dipole-dipole bond. Okay, so ethylene glycol has one location where it can hydrogen bond, but a lot of the molecule is structured so that it's just going to have like a London dispersion force because of that carbon chain that's nonpolar. And octane is a super long carbon chain. So what we see is octane has a larger London dispersion force happening than ethanol does. And so essentially the two kind of end up having almost the same surface tension. Okay, so sometimes I think when looking at a list of substances, it's hard just to predict exactly how strong the IMF is, but what we're mostly looking for is, number one, does it have a hydrogen bond, right, which water and ethylene glycol did, and then how big is it, because the size of it is going to start to affect the London dispersion force, and that London dispersion force will start to have a larger effect. The other property we'll look at here is viscosity. Viscosity is a measure of how, it says up here, a substance resists to flow. So I often think of it as the sticky nature of substances, how it's sticking to itself in relation to the ability for liquids to move, and how viscous something then is that resistance to flow. So harder to flow or flow, more viscous. So in my head, like molasses and syrups, those are all really viscous. Okay. Again, since it's a sticky quality, how well it's sticking to itself, that's all about IMF, how well it's sticking. And so if we look at, again, a couple substances here, we have that ethylene glycol again, as well as others. If you look at the viscosity and look at the type of IMF, you can see that there's a relationship. So ethylene glycol of all of these has two places where it can hydrogen bond, and it's pretty big, so it's the most sticky on itself, right? After that comes ethanol, which does have, again, the one place to hydrogen bond and has some London dispersion forces to it, so it's the next stickiest. Acetone is asymmetrical, so it has the dipole-dipole, so that comes next. And then diethylene ether up there is only London dispersion. And while the molecule is getting pretty big, right? So you're going to see a decent viscosity versus something that's only London dispersion that's smaller. It's less than all the rest of them. The other thing we can think of, because this is something that does happen with liquids, is how viscosity has a relationship with temperature. Okay? Some substances, as you heat them up, all of a sudden we notice that they run better, right? They're less sticky on themselves. And here you have a graph of that relationship of different oils and their viscosity. And what we notice is as they heat up, they're less viscous. Okay, so as we heat them up, they're less viscous. So why? Why would that be? Well, essentially, as we heat things up, we're increasing the motion of the particle, right? So we're allowing more IMFs to break. And if we allow more IMFs to break, essentially, we're not going to allow them to stick quite as well on themselves, and we're going to see more flowing. So hotter liquids tend to be less viscous than those that are colder, and that's because as the hotter they are, the more they move around, and so then they don't stick to each other. That's it for this video. Have a nice night.